Hey guys, welcome back to AP Precalc. This is lesson 1.9. Let's get right into it. All right, so for the bell ringer today, pause the video now if you haven't done it yet, because I am about to go over the answer. So we have a rational function, and all we want to know is the zeros of that function. So the first thing you want to do is find where is that numerator equal to 0. So that's going to be at x equals 0, 2, and 3. However, in the denominator, we have x equals 0 and 3 as zeros in the denominator. And remember, before we even find the zeros of the whole function, which is just when the numerator is equal to 0, in the denominator, right, you have to restrict 0 and 3 from our domain. We can't plug those numbers in, which means they can't actually be zeros here. So our only answer should be x equals 2. A is our correct answer here. So if you remember from last class, a rational function is simply two polynomials stacked on top of each other. And remember, we've talked about this both days, but the only thing you don't want to do with rational functions is divide by 0, right? Any number over 0 is a very bad thing, and it's so bad enough where we have to restrict those values from our domain wherever the denominator is equal to 0. So let's say we have just an example, x minus 4, x minus 3 over x minus 2, right? At x equals 2, this is where the denominator is equal to 0. So our domain should be all real numbers except x equals positive 2. That's our domain. We've learned that before. However, what happens graphically at this function when x does equal 2, right? What does that look like graphically? Because do we just like erase that part of the graph? What happens? And so today we're going to be learning about one of those two options, which is going to be either a vertical asymptote or a hole. And today we'll talk about vertical asymptotes. So recall from lesson 1.7, there's two different forms of an equation or of a rational function that you could see. You can see standard form or factored form. Standard form is used to determine horizontal asymptotes and end behavior, right? We've learned that, looking to see the degree of the top and the bottom, and then comparing them and getting your end behavior that way. Or factored form, which is going to be used in the next day and today in the next lesson to determine vertical asymptotes and holes. These two are very, very important and are what we're going to look at today. But basically, we're going to want every equation either in factored form or in standard form where we would have to factor it to get it in factored form. All right, so when does a 0 in the denominator become a vertical asymptote versus becoming a hole, right? Because it's either going to become one or the other. And so when a factor, not the degree, but when a factor is bottom heavy, it is going to become a vertical asymptote. All right, and a factor is bottom heavy in a few different situations. There's two that it could be. The first one is when it's in the denominator but not in the numerator. For example, if we just have 1 over x minus 5, that factor at x equals 5, or that 0 at x equals 5, or that factor of x minus 5, is not in the numerator. It's only in the denominator, so that factor here is going to have an exponent of 1 in the denominator, but not seen in the numerator, which makes it bottom heavy. The other option is it's both found in the numerator and denominator, but the multiplicity, not the degree, but basically is the degree of the factor, is higher in the denominator. So this is example 2. If we have maybe, let's say, x minus 5 over x minus 5, and this is cubed and this is squared, this would be a bottom heavy factor because it has a greater degree in the denominator than in the numerator. Right? So example 1, would x equals 5 be an example of a bottom heavy factor in each of the examples below? The first one is yes, right? It is found in the denominator, but it is not found in the numerator. So 1 should be yes. Number 2, if we plug if we take a look at that x minus 5 there, this has a multiplicity of 1 in the numerator and the denominator, so this would not be bottom heavy. It would in fact be equally heavy, and so this would be no. Here we see x plus 5 and x minus 5 is, the x minus 5 is squared, but this isn't even the same thing. So so don't get confused by that. We're only looking at x equals 5. So this is just found in the denominator, so this should be yes. And then the final thing here is this is a weird way to write a 0, but is still an okay way to write a 0, which instead of writing, x minus 5, you could write 5 minus x. And this is because if you plug in 5 for x, right, if you plug in x equals 5, you still get 0 here. That output is still 0. So this would also be an example of yes. All right, so now we're also going to get into new limit notation. So we've only learned so far how to describe a graph if your x values go to the right forever, or if your x values go to the left forever, right? We've only done the limit as x approaches positive infinity or the limit as x approaches negative infinity. We haven't done the limit as x approaches a certain number, but now we're going to do that. And so let's take a look at example 1. We see a piecewise function, and we want to know the limit as x approaches a specific number 1. But now we see kind of like an exponent, like subscript, but it's called a superscript, where we want to find the limit as x approaches 1, and then a minus of this function f of x here. And what does that minus mean? When you see the minus, that means coming in from the left, or the left-hand side. When you see a plus, that means coming in from the right, or the right-hand side. So here, as we come in from the left-hand side, as we approach an x value of 1, we're going to get an output or a y value of 1 as well. But when we have that plus, that means coming in from the right-hand side to x equals 1 right here, this is going to have a y value of positive 2. All right? Now, when vertical asymptotes occur, right, we know that occurs when a factor is bottom heavy. However, what does it look like graphically? Vertical asymptotes graphically are going to look, let's say we have one right here. Basically, when you go to that value, that function is either going to shoot up to positive infinity or it's going to shoot down to negative infinity. We can write this behavior in limit notation, which is our way of describing how the function approaches any value, even if that value doesn't exist. And so example number 2, write the two correct limit statements as x approaches 1 from the left. So remember that minus means left-hand side, and from the right-hand side as well. So as x approaches 1, as we come in from the left, we see our values are going down. So the limit as x approaches 1 minus, which means from coming in from the left, should be, it's going all the way down to negative infinity. And as we come up to the right, or come in from the right, this is going up. And so our limit as x approaches 1 plus should be positive infinity. So at a vertical asymptote, though, if we have that, let's say I graph a vertical asymptote right here. If we just have a random function like this, it will always either be positive or negative infinity. It could be flipped. You don't know how the graph could look, but you know it's either going to be positive infinity or negative infinity for limits as x approaches a vertical asymptote. Now, how do we actually know as x approaches a vertical asymptote whether it's going to be, let's say we have a vertical asymptote right here, whether it's going to look like this or whether it's going to look like, sorry, let me redraw that. If we have a vertical asymptote here, whether it's going to be going down from the left and up from the right, or it could even look like this where they both go up, right? So how do we know what direction they're going to go in? And so it's pretty easy. We're going to plug and chug. And so let's say we have, let me draw out a graph, y equals 2x over x plus 3. And so this is going to have a vertical asymptote at x equals -3. There we go. And so how do we know what it should look like? Well, graphically, it's going to look like this. But how do we know that? And it's pretty simple. What we want to do is, obviously, if you plug in x equals -3, you're going to get 0 in the denominator, and you can't do that, right? That's why that vertical asymptote exists. But what we can do is you can plug in a value that kind of hugs that graph. So let's say we plug x equals -3.001, and we plug in x equals -2.999. What we see here is if you put it in, right, you're going to get a weird number, right? It's either going to be super big or super small, but it's not going to give you a domain error because you're not really dividing by 0. You're dividing by -0.001 or positive 0.001, but you're not dividing by 0. So you can plug those in, and this is where you'll need your calculator. Use your calculator to just evaluate that number and basically see if it's going to be a really big number. Like let's say you plug in x equals -3.001 into 2x over x plus 3. You should get 6002 as your y coordinate, which means if we plug in this x value, we're going to be basically going up to positive infinity. And if we plug in -2.999, you're going to get a y coordinate of -5,998, which is basically going to represent negative infinity, right? So this is negative infinity, and then this is positive infinity, and that's going to be how you can determine the behavior as it approaches that point. Now, obviously, I would never expect you to plug these values in without giving you a calculator, so don't feel like you have to do all these with no calculator because they're rather difficult to do so. All right, so this is just a recap of vertical asymptotes. Remember, vertical asymptotes occur when a factor in the denominator, so it has to appear in the denominator, cannot cancel out with factors in the numerator, meaning it is bottom heavy. Once we have this, two examples are these two functions here. This one at x equals 1 is only in the denominator, and then this one, the degree is just bigger in the denominator than the numerator. And this is what it looks like graphically at x equals 1 to have that vertical asymptote right there. And as you can see, one goes down and the other one goes up. Right, so example 3, for each of the functions below, determine the x values of any vertical asymptotes. So this, we see x plus 3 is in the top and the bottom, but it's equally heavy, which is not the same as bottom heavy. So we can eliminate that from being a vertical asymptote. The other one in the denominator is at x equals 5. This should be a vertical asymptote. Here, x equals 2 is going to be top heavy. It has a higher multiplicity in the numerator than the denominator. But at x equals -1, this should be bottom heavy. Negative sign in there. Because the degree is bigger in the denominator than the numerator. Here, if we factor c, you should get g of x equals 1 over factoring out an x squared plus 4, which is 1 over x, and then we actually can't factor x squared plus 4, so we can be done there. Here, obviously, we're going to get imaginary solutions here, so you don't really need to worry about that. Our only solution should just be at x equals 0. Should be our vertical asymptote there. All right, so now what we want to do is we want to write a left and right hand limit statement as x approaches 5 for each of the following functions. When we're looking for the analytical ones, the equations, we can just plug in 4.99 and 5.01, and those will be close enough to be okay. So let's take a look at the left and the right hand limit statements for a and b. Now remember, if we are approaching x equals 5, on the left hand side this should be 4.99, and on the right hand side should be 5.01. So for the left hand side, let's first plug in 4.99. You should get in the top 3.99 times 7.99 all over negative 0.01. And then this should give you negative 3,188 around. So 3188, let me write that a little nicer as well. Equals negative 3188. And so this is going to be negative infinity. So if we write that limit statement, we would write the limit as x approaches 5 coming in from the left of f of x equals negative infinity. On the right hand side, if we plug in 5.01, we get 4.01 times 8.01 all over 0.01, which is around 3212. And so this would be the limit as x approaches 5 coming in from the right hand side of f of x equals, and this is going to basically be positive infinity there. Right? So these should be our two correct limit statements there. The next one, by plugging in 4.99 on the top, you should get negative 0.01 times 8.99 all over negative 0.01 squared times 1.99. This, when you spit it into your calculator, you should get negative 451.8 around, which means we can write our limit as the limit as x approaches 5 coming in from the left of g of x equals negative infinity. So that basically is going to be negative infinity. If you ever aren't sure, just plug in like 4.999 and like just make it closer, but that should be a correct limit statement there. And then the right hand side, plugging in 5.01, you get 0.01 times 9.01 all over 0.01 squared times 2.01, which is going to be equal to 448.3 around. So this is going to basically be positive infinity. And so our limit statement is going to be the limit as x approaches 5 coming in from the right of g of x equals positive infinity. And that should be our two limit statements there. C is a lot easier, right? You're just looking at a graph. And so the left should be the limit as x approaches 5 coming in from the left. This is, as we come in from the left, this is going down. So we'll call this h of x equals negative infinity. And then on the right hand side, as we come in from the right, this is going up. So the limit as x approaches 5 plus of h of x equals positive infinity. And those would be our two limit statements there. All right, if you have any questions, please come see me during office hours. I'll see you guys later.